So I'm going to show you a couple ways that you can use DFS. So this is going to be more of like a brief exploration of these things. So I thought I would start off with a simpler one based on our discussion on depth first search. So let's talk about some applications. So these are some classic things you can do with the depth first search traversal. These are not by any means the only ones. There's many. I mean, so many out there that I could easily spend a whole afternoon at minimum just highlighting some of them to you. Here, I'm just going to do a couple. Some are far more classic than just these ones. So the first one, I thought it would keep it simple. Let's talk about cycle detection. So suppose that you want to detect if there's a cycle in your graph. Another way you can look at this is that if I want to know, if I give you a graph, is it, for example, a forest? Like, how do I know if my graph consists of a collection of trees? So one way you can do that is detecting a cycle. And now, one thing that's really natural about exploring a graph using DFS is, let me show you a very contrived and simple example, but it makes my point well enough. So suppose that I have a very basic graph that looks like this. That's 4 vertices, and it's just going to be a box. Now, I'm not going to make it the box graph. I'm just going to make a box that looks like this. So notice that this actually consists of a cycle. This is an example of a cycle graph. It consists of 4 vertices. Some would call this, I think if you count it by vertices, I think it's called C4. But we have 4 vertices here. There's one cycle right here. It's the whole graph. So notice here that if you use DFS, suppose you started at U, well, what you would do is you would go through the following process. Let me just remind you of how this would work. So you'd mark this vertex. You can go down this way, for example. It doesn't matter. You can go this way. It doesn't matter at all. I'm going to mark this vertex. I'm going to consider my incident edges. Notice I found one that's unlabeled. I continue down that way. I mark this vertex. I consider my incident edges. Then I find one. Oh, look, there's one right there. I'm going to mark this vertex. I consider my incident edges. Notice I have one that's not labeled here, right? Well, what would I label this edge as? A forward edge or a back edge? So would that be a forward or / discovery edge? Or would it be a back edge? Well, look at it. If we are at this vertex currently, but the opposing endpoint's already marked, so that means it's going to be a back edge. A back edge. So that gets labeled as a back edge. So notice here, the reason why we had the back edge is because this vertex already was marked, right? So that means that we have actually a nice, very simple way of detecting a cycle. Why? Because think of it. We already were here, right? So to find a back edge means that I found, if we go back to our analogy about finding our way through a maze, it means I already went down this passage already. So I already went around this way. In fact, I can construct a cycle by following these forward edges to the back edge. So I can form a cycle constructively like this. So the presence of a back edge, I can use this to detect a cycle. So just to kind of summarize what I'm saying here, just to summarize, the presence of a back edge it's saying that the graph is cyclic, meaning it has at least one cycle in it. So any cyclic graph has a back edge for its DFS traversal. So that's actually how you can detect a cycle. So let me show you how you could write this in some pseudocode. So I'm going to show you how you can augment DFS to do this. So the thing I really like about DFS is that just like when you talk about some other things like tree traversals and things like that, they work like a framework so that you can pick it up and you can say, hey, look, I want to adapt it to solve this other problem. So if you understand the underlying structure of type for traversal you're using, you can try to see if you can take advantage of properties it has. In this case, it is the way that the back edges and forward edges get labeled. So if I could take advantage of just simply determining when this back edge gets labeled, that tells me if there's a cycle or not. So the minute I label a back edge, I know there's a cycle. So I'm going to call this algorithm hasCycle, and I'm going to have some starting vertex. I'm going to presume the graph is connected. Otherwise, you can adapt the idea that we talked about previously, where you just simply we bootstrap the algorithm again with another unmarked vertex. So I give you a vertex of a connected graph. And I'm going to make it so it's just simply going to detect the cycle. So it's just going to tell me there is a cycle or there's no cycle. So it's going to return true if there's at least one cycle, false otherwise. So it's true if there's at least one cycle, false otherwise. So here we go. So watch this. So do you remember the process for DFS? Remember, we mark ourselves and then we consider our incident edges, right? So that's what we're going to start off with. Because the fact we are marking vertices actually matters here, because that's how we use as a mechanism to know if we need to label a forward edge or discovery edge or back edge. So I'm just going to write out for each incident edge, we're going to go through each one of the incident edges. Each one of them. And then we check if it's not labeled, right? So if UV is not labeled. So the main reason why I'm writing it like this is so that you can see how you can adapt DFS. So like I said, I like to think of DFS like a framework that you can pick up and use to solve other problems. So here we go. So if UV is not labeled, then we had our two cases, right? We check if V, the opposite endpoint, is marked or not, right? We know that when it is marked, we're going to run into that back edge. So if V is marked, then we're going to label UV as a back edge. So I must stress, by the way, that it doesn't really matter a whole lot what we label the edges. What really matters is that we find a back edge. Just the condition of a back edge is that the opposing endpoint is marked. So if we run into this back edge, meaning that the opposite endpoint's marked, we return true. Otherwise, we're going to continue our search. Otherwise, we're going to label UV as discovery edge or forward edge. As discovery edge, then we just check. Now you might ask, Dan, how exactly do we just stop the algorithm from continuing to do the search? Well, I'm just going to do the following. I'm just going to put the recursive call in my condition check. Notice that this returns true. It's a Boolean value, so I could just simply use that for my logical test. So here's one way I can frame this. I can say if hasCycle, which is the name of our algorithm here, if hasCycle and I pass it along V, returns true, then you can return true. So this will prohibit you from continuing your search as soon as you find a cycle. So let's see, I just want to make sure I got everything all sorted out. We need to, wait, I have it right here. No, wait, that's for that. Always got to be careful. I have the closing brace, so that's for this. That's for that. And naturally, I need to close everything else up. But after the loop, This is the part that really matters. Is how do we know we don't have a cycle? Well, that means that I had to have examined all of my incident edges and I didn't find any more options but to say I didn't find a cycle. But I will not know this until I've examined all of my incident edges to see if I've encountered an opposing endpoint that is already marked. Does everybody see that? So I can't conclude that my vertex is a part of some cycle, or at least one of the cycles, until I've examined all my incident edges. So after the for each loop, this is when you would return false. And here's the beautiful part. Notice that if you still think about it, in the worst case, you're still going to have to examine all the vertices in your graph. And all the time complexities we talked about in our analysis of DFS, they still apply here. This is the beauty of just adapting DFS. I said, everything we did to change it doesn't affect the overall time complexity from an asymptotic standpoint. It's just that all I did was I made it so that there's a little bit of a just a little shortcut when we actually find the cycle, or at least one of the cycles. But yeah, so this is how we can do a cycle detection. I must stress that you can augment this with the second application I'm going to show you here if you actually want the cycle. So let me show you the next one here. So that brings me to talk about pathfinding. So how do you find a path in a graph by adapting DFS? How do we compute a path using DFS? So let me just take this and we're just going to take it one step further. So here we go. So I must stress that we could take DFS and adapt it in many ways. This is just one way you can do it to adapt to find paths. I'm not claiming this is the only way you can find paths using DFS. It's just one way of doing it. So for the sake of completeness, I'm going to mention to you that I'm just going to presume that I have globally accessible to me a stack. Now, this could be, if you're actually taking this and picking it up and implementing it, you can imagine this like you have some class, for example, if you're using an object-oriented language, you can imagine this like an instance variable in your class, or even a static variable, if your language supports that. So my presumption, I'm going to presume stack P is empty and accessible to use. So you can think of it as just a global variable if you have a language that supports global variables. The point is it's some stack. And if you remember our discussion from depth first search, you'll remember that I illustrated that when we explored the graph, the string that we used to examine the labyrinth, it corresponds to the stack. So if we make our own stack and we keep track of the path, which represents the current thread of string that we're examining with, then we can actually get a path. But the thing is, I need some way of stopping the search as soon as I find the path, as I alluded to when I was discussing that algorithm. So what I would like to have happen is I would like to have this stack store this path from two desirable vertices, a vertex S and a vertex T. So we want a path from S to T. So these two are vertices, and we'd refer to this as an ST path. So let me give you an example of, just to walk you through DFS, just to see where we can get the idea from, like how exactly did this work. So let me give you a pretty nice, simple example here. I encourage you, by the way, if you want to pick up another example and play around with it, please do so. I encourage you to walk through this carefully. So here we go. So suppose I have the following graph. I have A, is going to be our starting one. So I'm going to make it S. Convenient, right? So we have A, B, C, D, and E. And suppose that I would like to find a path. Actually, let's throw another vertex in here, one that most certainly I cannot reach, like F here. Notice that there is, like if I want to go from S to F, that's not happening. There's no path there. So let's think about this. So what I'm going to do is I'm going to take advantage of having this stack P. This is going to be my stack. I could play around with it. So this is stack P. And suppose that I want to find a path from A to E. Now, I must stress that this example is just meant to illustrate the idea. The graph may be much more structurally complex than this. Because this, for example, the structure I have here, technically this is a forest. There's only one pathway from A to E. But it doesn't matter in this at all. So, anyways, let's walk through DFS. I want to show you how I can use the stack just to illustrate the importance of why we needed this string to help us unravel to examine the labyrinth and wind it back up when we hit a dead end. So let's walk through this again. So I'm going to mark this vertex, then I proceed to B. I mark this vertex, but remember, what I would like to do is I would like to find a path from S to T. So I start off with A on the stack. So I'm going to push that onto the stack. And then I go to B. Now B may be potentially a part of the path from S to T. So currently I'm at B. So I'm going to push B on here. Now I'm going to consider my incident edges if I'm not T. So notice this isn't T. So I need to keep looking. So suppose that I go this way. Suppose I go to D. Notice that D, there are no more incident edges for me to examine. So that means that I know that there's not going to be, this isn't T, right? So I know this is not going to help me. So I'm going to go back this way. So I'm going to go back up, back to B. So I'm back to B. And now I consider another incident edge. And now let's go to C next. So I got 1, 2. This is the next one we're going to go to, 3. After going to, actually, let me number these all in entirety. So we visited 3, then we visited 4. Keep in mind, it doesn't matter that we went to D before C. In the algorithm, it doesn't make any difference. The point is it could. But notice that we didn't go there at all. The T's not going to get us from here. We ran out of options. Now next we mark C. And then we follow along here. And we get to E here. After we mark it. Now the big thing. Notice that now we found T. So that we can stop our search. Oh yeah, I need to also make sure we push E onto the stack. When we mark it, we would probably want to push it. Now, if you look carefully at our stack here, notice just like what we talked about previously when we looked at where presently we are with the string we are using to examine the labyrinth, notice here that if you read this from bottom up, there's your ST path right there. A, B, C, E. A, B, C, E. So if you just take this backwards, you get exactly the path. Does everybody see that? Fascinating stuff, right? So this is actually how you can store the path that you find using a stack. So if you make your own stack, you can take this and adapt DFS to find your path you're looking for. So let me write out the pseudocode for this. Nice and simple stuff. Let me just move over a little bit this way. So we're going to try to see how this would translate into DFS. So notice that all I really did to change up DFS was I checked if the vertex I was at was T. And in addition to this, after I do this, if I fail to find t, I'm just going to do what I did with DFS anyways. Just the point is I have this stack I'm going to have to maintain. Well, what happens when I hit a dead end and I run out of options and it's not t? This is when you're going to pop the stack, just like I did my example here with d. So I'll show you how this is going to play out. So I have vertices. So now we're going to be given vertices. So let me give ourselves a nice description here. And I must stress again, this is not the only way you can do this, but most certainly this is a nice way you can see how you can take DFS and find paths with it. So for example, you could take this whole algorithm, make it iterative, for example. You'll see that I'm just going to make it so it looks like the DFS I showed you earlier. So I'm going to presume I'm given two vertices, S and T. And it's going to output true if there is a ST path. False otherwise. The point is that the stack P will store the path after when I'm done. So if you're wondering, where's the path, Dan? It's in P. So you just go look at P. You could pop off the path when you're done. So remember, like we usually do, we mark the vertex. So we mark S. But you're going to feel, here's the neat part. When we do this, you're going to see it's almost like S is going to move along with our exploration. So it's almost going to, like we're hand-holding S to T if there is a path. So that's sort of how you can look at the recursion that you're going to see here in a moment. But it's not literally that. To just be very clear. So we're going to push S. And as I said, we're going to check if S is equal to T. If it is, then we're going to return true. That means we're done our search. Otherwise, we consider all the incident edges for each SU. We're going to do the following. Now, one thing you can do with DFS, you notice how, like, here, it didn't really make any difference if the edges were labeled or not. So let's just not care about it. So this is another thing you can do with DFS and all these other graph traversals, that if it's not relevant to label the edges, you don't have to. Just like if you really care about the edges, but you don't care about the vertices, you may not necessarily need to mark the vertices. Depends on what you're trying to solve. But the point is that you can strip away those details if you need to. So if U is not marked, because remember, we want to make sure this thing actually terminates in finite time. We need to make sure we don't simply keep redoing the same work over and over again. If U is not marked, then all we're going to do is we're just going to call recursively pathfind. So we're going to use the same trick we just did a moment ago. If pathfind, and I call it on U and T, so I'm going to advance it one step forward at this call. So pathfind UT. If I'm successful at finding the ST path, then I'm going to return true. Then we return true. Then that's the end of the for loop. Now if I run out of incident edges to examine and I fail to find the ST path at this stage, keep in mind this will take me all the way there if I need it, akin to what we discussed previously. If it fails to be the case that our node actually advances us to that search, we're going to pop it. We're going to pop off that node, and we know that we've hit an end that is not going to get us to T. So we return false. And that concludes the algorithm. And again, like I said, all we've done is we just took out elements of DFS. Everything else that we did here, pushing and popping on a stack, can be done in constant time if we presume the appropriate representation for the stack. If, for example, you're using a linked list for your stack, these two operations here will take constant time in the worst case. If you know how many vertices are in your graph, even using an array-based implementation will be good enough if you know how many nodes there are in your graph, which is something it's easy enough to keep track of as some instance variable. But yeah, no, so this is how you can adapt to find a path in a graph using depth first search.